Okay, just a quick reminder. We are using Mercat app for Q&A session, so please prepare it ahead of time. And the panel will be 45 minutes, and we have 10 minutes secured for Q&A.
Great, thank you. Can we? Awesome. Thanks, everybody, for being here. So yeah, we are going to be here talking today about formal verification, which is a topic that I think all of us love a lot. The chat already before has been intense, so that's good. So yeah, so we'll start, I think, just start by introducing everybody. So we'll just go around and just everyone to give us a bit of a background of their, background in formal verification and the kind of thing that they work on. So yeah, so maybe start with Julian and we'll go around.
Yeah, so my background is I actually did, my initial focus was I did a PhD on formal verification for concurrency. I was looking at termination, so, very, very different concerns from what we mostly focus on in Web3. But after I finished that, I came to work at Nethermind, and yeah, it was sort of, it's a very interesting system where there is actually a lot at stake, while in some ways, some parts of the system are relatively tractable and so can actually be verified. And so I was really excited to be able to contribute to that, and in particular, try and apply hard formal methods to try and really get the highest degree of certainty. And that's, I guess, what my team focuses on.
And just to clarify, the tools that you use mostly in your work?
Oh yeah, so we primarily use the Lean Proof Assistant and EasyCrypt. So these are very. Should I add a little bit about, or we wait till later? Oh, okay. Cool. Yeah. Sorry. Go ahead.
So hello, I am Zoe. I did my PhD in compiler verification, and for this part, I mostly used proof assistants, in particular Calc. And for the last couple of years, I've been working on building tools for verifying smart contracts. And for that part, we use a combination of proof assistants and SMT solvers to automate verification tasks. Yeah.
And you're part of the Argo Collective as well.
And I am part of the Argo Collective, the recently formed Argo Collective from former EF employees who are building languages and tooling for the Ethereum ecosystem. And I'm also an assistant professor at National Technical University of Athens, where I specialize in programming languages and verification.
Cool, thanks, Zoe.
Hi, I'm Igor Konnov. I'm an independent researcher now. Previously, I worked in the Cosmos ecosystem for 4 years, so I'm not new to blockchains, but I'm kind of new to Ethereum, actually. And my primary tools are model checkers. I'm a model checker guy, using explicit state model checker, checking symbolic state model checking, but also simulations, randomized stuff, and things like that. So, yeah, I worked on model checking of Tendermint consensus, for instance, checking some property there, checking agreement, accountable safety. Also worked on verification of smart contracts, but that's not the coolest thing I have done. And this year we actually had a project with the Ethereum Foundation on checking accountable safety of the new 3-slot finality protocol. Yeah.
Great, thanks, Igor. Okay, so we've got a few questions that we're sort of going to go through, and there will be a Q&A session at the end. Don't forget to post your question, if you have questions, post them to the QR code, and then they will be read out at the end. Okay, so yeah, so the first question, which is, I think, possibly my favorite question, is about tooling. And so I'm really interested to know, the tools that you use, and in particular, what you think their strengths and weaknesses are. Where are they do they work really well, and what are the pain points that you're really feeling? So I don't know who would like to start with that, or we can just go around.
Yeah, I'm happy to start, yeah. So as I mentioned, we use a combination of Lean and EasyCrypt for very different things. EasyCrypt is a domain-specific proof assistant, which we use primarily for cryptography verification. And then Lean is a general-purpose proof assistant, which actually, well, this is a bit debatable, but I would say that it has the largest formalization of mathematics in existence. Hull users will obviously be screaming at me; they're wrong. So the reason that I say that is that the Hull library is not very well organized. They have a lot of theories.
Maybe it's the largest coherent library. Of
Exactly,
methods.
the largest code. So Hull is very disorganized. There are lots of like replications of theories with slight differences, and then proofs that say, hey, these theories are equivalent, so you can like cast theorems between them and these sorts of things. But so technically, it has more theorems, but as you said, not really cohesive. So there you go. So yeah, and Lean. So our goal with both of these is basically to actually be able to verify. And I imagine Igor, you'll talk about this more about automated theorem proving and these sorts of things, of course. But our goal there is to verify, I guess, the really complicated parts of the ecosystem. So we look at verifying like complex safety and liveness properties of protocols. We look at verifying cryptographic safety properties, these sorts of things, which are things that typically are too complex for automated theorem proving to be able to easily approach without a significant amount of guidance, essentially. So
Where are the pain points that you've sort of hit?
excellent question. So EasyCrypt has access to SMT solvers and these sorts of which typically allow us to automate away these sorts of like small detail things of like the practical implementations of programming languages, like hey, the sum of these 2-bit vectors doesn't overflow or something like that, right? And in proof assistance, typically reasoning directly about these things, mostly because actually until recently formalizing these sorts of things haven't been a big concern in proof assistance. So it can be quite painful. And in fact, when we were working with RISC-0, we had one engineer working for 2 months continuously on formalizing a bunch of theorems about bit vectors, and most of them were just like through brute force unfolding, and it was extremely painful. And a lot of these things can be done in like minutes or hours with the right SMT solver. And then all of that broke when Lean's mathlib changed the definition of a bit vector. So, but anyways, they've since improved that library, and now we don't need to do that anymore. But that was a painful moment.
Yeah, that sounds challenging.
That was unpleasant. Yes. Yeah.
Thanks. Sorry.
I use a combination of proof assistance, in particular COG, and SMT solvers. Both are great in their own ways. The good with proof assistance is that whatever can be proved, you can prove, like sky's the limit, the user's ability is the limit. And SMT solvers are great because they can automate very tedious tasks that they would be very hard for the proofs to go through otherwise. And they can be used for like symbolic execution, for instance, which is very useful, like to find like assertion violations or potential errors in the code. This is extremely useful, but then if it doesn't work, then there's not much you can do about it. Yeah.
So comparing that then to the interactive theorem provers, like, what is the challenge that you find there?
In theorem provers or in SMTs?
No, in interactive theorem provers.
In interactive, the proofs are hard. Very hard.
It's the time that it takes to actually get the proof through.
Yes, it's like it requires a lot of like expertise to like carry out proofs in proof assistance, to encode problems, to encode specification problems in proof assistance. So it's time consuming, and but it's also very rewarding for a proof to go through. So yeah, another interesting difference is that in proof assistance, you build the proof is there forever. You can take it at any point. SMTs will not, in general, produce a proof that is checkable. So you need to rerun the SMT every time you want to prove something, which can be like time consuming in terms of resources, computer resources, and also like it can introduce some non-determinism.
Yeah, I mean, we've certainly had experiences where upgrading to the latest version of Z3 has meant now the proof doesn't go through, for example.
Exactly. Yeah.
Right. Awesome, thank you. Igor?
Yeah, I'm using CLA Plus as a specification language. That's temporal logic of actions by Les Lampert. He invented it like some decades ago. And there are like actually several tools there. One is an interactive theorem prover called CLAPS. I don't use it much. I'm not the guy who can write proofs for provers, basically. But there is also an explicit state model checker, which just enumerates states. And if it terminates, it's good, right? You have proven the property. If it does not, what do you do, right? And in most cases, if you are dealing with something like consensus, it never terminates, right? Because the state space is huge. The Byzantine faults introduce a lot of new states and everything. And like there is a third tool which I have been developing for since 2016. It's called Apalache. That's a symbolic model checker. It translates TLA plus into SMT. But many of you guys, I guess, imagine quantified SMT and everything. Our translation is very stupid. It actually removes all quantifiers. Everything is like
It's
grounded.
bounded, right?
It's bounded model checking, yeah. There are only constants. And we just analyze executions up to like 20 steps or something like that. If you're smart, you can use induction there to reason about unbounded executions, but that's kind of hard because you have to invent inductive invariance, which is as hard, I guess, as proven at some point. Yeah, and like the strengths that you can just run it, right? You just wrote your spec, you push the button, it runs. The weakness is that it can run for days and you have no idea whether it's going to terminate or anything. So basically there you have to apply a lot of tricks, like introduce additional abstractions. If you see it even doesn't work for simple things like reaching interesting states, you have to introduce abstractions, make it faster, observe like which of the transitions take a lot of time in SMT and all of that.
So it feels like you do spend quite a lot of time sort of trying to tweak those parameters to help the proof go through.
Yeah. And I guess like the main benefit that you're trying to find bugs as fast as possible with these tools. So you really start with very small input space to like trigger, interesting behaviors to find problems. And then when you're convinced it kind of works, you start increasing the state space and see what happens.
Cool, thank you. Okay, so next question. So I think this is one that maybe the audience might appreciate as well. So what are the challenges that that you have faced in getting formal verification to be adopted, within your organization? I think that's the first bit, but also in a kind of broader sense within the community, because I certainly feel that there are a lot of challenges here.
Yeah, so I think in Web3, one of the key issues is that the technology and the space are moving so fast, and everything we do has a very high cost in terms of tooling. It takes a long time before you can develop formalizations of the new languages, the new systems, etc., so that we can actually practically verify things. And that's, I think, true whether using interactive or automated theorem proving to some extent. And so the thing is, it certainly feels like I'm playing a bit of a guessing game sometimes as to what is actually going to be useful next to figure out where I should actually be applying my team to actually develop new tooling. And it's happened a couple of times. I think I can think of 2 instances where we have invested like 6 months plus of work in a tool only for it to be essentially deprecated the moment it's released. So, I mean, this happened with a tool that we had that was called Horus for Cairo 0. Which was the first Starknet language, and literally, I think a week after it was released, Starkware announced that there was this Cairo 1 language going to be released, and Cairo 0 was going to be deprecated, and we spent 6 months developing that. That was pretty painful. So,
I can imagine. That sounds, yeah, very unfortunate.
Yes. So there's that, and then I think, I mean, this is more true for the kind of techniques that I use, where our techniques are not necessarily. So I mean, we were talking about, the difficulty in embedding things into interactive theorem provers, and there's truth to that, but also it's also true that, modern interactive theorem provers, you can embed all sorts of automation into them. And, if you find the right set of automation, you can make things a little bit more generic, a little bit more, well, much more robust in theory. I mean, there are examples of, for example, the verification of Cairo, which is written in Lean, actually. Apparently, I mean, the details are not all public, but this has been developed by Jeremy Avigad at CMU, and the proof generation is apparently almost entirely automated inside of Lean. So there are sort of some interesting things. Interesting things you can say that you can do in that direction. But there is a difficulty with robustness, where like with clients change implementation significantly, we have to redo a lot.
And presumably, it's not just you mentioned languages, but presumably it's not just languages. So I know that you work in the ZK space quite a lot, and so it's actually new algorithms as well that are coming along. You've got Plonk, Turbo Plonk. There's all these different things coming out, and so it takes a lot of effort to understand them. And
to understand them and to understand, hey, what are the properties, semantics they enforce, etc. and also because we're doing verification on the cryptography side, like what are the cryptographic guarantees, what are these sorts of things. So yeah, I spend my life reading papers on a variety of different things. So there you go. Yeah.
Well, it's
It's
worse
interesting.
things you could be
Yeah,
doing.
the worst jobs to have. So.
Cool, thanks, Julian. Zoe.
So, as Julian said, yeah, it's very time consuming and there is a steep learning curve, even within experts, to go from one tool to the other. So if there is a team working and formally verifying something with a tool, then like abandoning the tool and going to something else, it's going to take a lot of time. But there is also a lot of maintenance burden. Like it's hard, you build something, then the code changes, then you have to adjust the specification, the verification. That can also be very hard.
Yeah, sort of like maintaining the proof alongside the artifact itself.
Yeah, exactly. And things change quite quickly in this space. So yeah, that can be tough. Yeah.
Do you feel like there are any strategies to help kind of mitigate that? You know, like to make it easier to maintain as artifacts change, or?
So I think programmers should program with verification in mind, or at least specification in mind. Like I think there is a lot of value to writing specifications. Even these are not going to be formally verified, they can be tested. I mean, there is property-based testing. We can test specifications, and that's actually quite useful and productive in terms of code quality.
Okay, cool. Thank you. Igor.
Yeah, I mean, when I started working at the company like 5 years ago, you know, doing stuff for Cosmos, I talked to a lot of engineers, and actually I expected them to complain about performance and all these things, but it wasn't the case. They complained about usability. It was basic usability. I was showing them TLA+, and if you have seen it, it's kind of LaTeX-like, Muzzy syntax. And there were all kind of questions like, what does this thing looks like? What is this mountain doing here? What is like, kind of strange questions, but usability was #1 issue there. You know, like what do I write? How do I write it? Why do I write it this way? Why don't I write a loop? You know, all this stuff. So I think it's the #1 issue there. And at some point we even introduced the surface syntax for TLA+ that looks like a programming language, and that changed a lot. People stopped complaining immediately. They were saying, okay, this we understand, that's fine. Oh, that's TLA+, that's fine. It's like very good. So really, like focusing on usability, I think is #1 thing.
So kind of connecting to what people already know makes a big difference.
Yes, exactly. If people come, if they even have seen like a simple functional language, it's much easier for them to connect to what TLA+ is, unless they have been writing proofs in math, you know, which is very unlikely if you're talking to engineers. So that's one thing. And another one, like what you already mentioned, it's kind of time to value. You know, if you tell them I spent like 3 weeks writing a specification and then I check it, they will be super disappointed because at some point maybe it doesn't check, you know, nothing happens. And it's very important to give them results like on day one. Basically, you start writing the spec, you tell them, look, I can generate an example. I can show you an example where you know, an algorithm reaches some state. And I'm super excited about it because before that they were drawing it on a whiteboard, which is super time consuming. If you can generate an example like in 5 seconds and they can read through, it's amazing, you know? So time to value is super important, and like randomized exploration, I found it super useful. Before you try to do any proofs, just try to
sort of find that low-hanging kind of fruit.
Exactly,
really.
exactly.
Yeah. And do you feel like, you know, there's a challenge here in getting people to appreciate the value of formal verification? I mean, I feel like that's sort of what you're talking about there, that helping them see results quickly will help them see the value.
Yeah, I guess it's a bit even more than that. I think it's kind of a problem of trust, because if you write a program, you kind of can run it and get your confidence in that it does something useful. If you write a specification, it's just a piece of text, and it's hard to understand whether it makes any sense. The same for provers, I guess, right? Unless you prove something, right? And it's really, you have to give them a way to gain trust in this artifact very quickly. And whatever execution, random simulation helps a lot. It's really because for them it's kind of a detached writing on a wall, which is not running. And they're all engineers because they're used to running things. So I think it's kind of, yeah.
Okay, thanks.
You know, if you don't mind me just
Sure, sure.
interjecting, the analogy that I've actually used for it fairly often is that I feel like actually formal verification suffers from a lot of the same problems that vaccines do. In this, genuinely, in the sense that, as I said, people don't really understand them, right? And the thing is, if they work correctly, then nothing happens. And, right?
Yeah.
No, genuinely, if we do our job right, the point is nothing bad happens.
And you never feel like you needed to do it in the first place then, right?
Yeah,
That's the
exactly.
thing.
Maybe nothing bad would have happened if I did nothing. You know, you don't know. So.
Yeah, I see where you're coming from there, yeah. Okay. So this, I feel like this is, yeah, okay, pretty similar or sort of related question. So obviously formal verification is often seen as quite difficult and costly to apply. I think we've already kind of covered that, something like that. But I guess the question here really is, you know, as a community, what can we do about that going forward? How can we try to lower those costs? You know, what are the things that we can do? And I think Igor already did touch a little bit on that, but interested in more thoughts that you have. I don't know who would like to go. Yeah, Zoe, go. Yeah.
I can go. So as language designers and implementers, I think we should build languages and tools with verification in mind. So once you have a language that has like integrated support with verification, then things will become much easier for programmers to like get used to, adopt, trust even. Like languages, for instance, with support for, like, but real world languages, not just like very niche languages that are used in academic environments, but like real world languages with support for writing preconditions, postconditions, having rich type systems, like being able to write invariants, even if they are not proved like automatically or directly, even if they are tested, there is a lot of value to it, to like for people to learn the discipline.
Yeah, so we were talking about this actually yesterday in the formal verification hangout, and in particular talking about Solidity. And Solidity has this kind of extension called Scribble, where you can write pre and post conditions as comments. So, you know, it seems to me, you know, what you're suggesting there, it would be really nice to see that kind of solidified and turned into part of the language itself.
Yes, exactly. And then it will be easier to reach more people. It will be easier, like, for people to think about it when they write code, which is extremely important to make formal verification, like, viable.
Great. Yeah, I actually completely agree with that. I think, you know, using some lightweight methods just to help people get into it and to see the value and to catch that low-hanging fruit, I think that definitely is a win.
And I think success story is Rust, which has like very rich types. Types is verification basically, and it's widely adopted and like people love it. And I think it will be nice to have more examples like that, even for like languages compiling to EVM.
Cool. Igor? Yeah.
Yeah, I mean, what I wanted to say. Yeah, I mean, really providing faster feedback loops is that what we could do, you know, to give value to the users, but also maybe the community could help us explain what they do not understand, because it's also maybe people are a bit afraid of saying it because it all looks complicated, PhD level stuff, you know, and people should be just upfront saying like this I don't understand and this doesn't work for me. Maybe you should simplify it. I had conversations like that. It's sometimes it hurts, but it's very useful to hear it actually.
Yeah, I mean, I definitely agree. You know, academic papers in particular can be very hard to read and understand. And even coming from me, I've got that background, right? You know, so yeah, anything that can help bridging that gap. Yeah.
But also having like open conversations like we have now about what works and what doesn't. That's super useful.
Cool. Julian, yeah.
Yeah, so the following in the same vein, I think, yeah, accessibility is super important. One of the things that we've done actually is writing property testers that allow us to extract, well, what do you call it? We've written a property testing extractor, essentially, from specifications that we write in Lean. So we can write specifications for a smart contract, and as long as they're decidable, we can automatically extract a property tester from it.
So like input values, for example.
Yes.
Is that what you mean? Yeah.
Yeah. So basically, it gives you like a generator for input values, and then a relationship, a decidable relationship between the input and output states, and then we just run it on an execution client and see if it's satisfied. Run the decide function, and so yeah, having this sort of feedback. Being sort of, developing these specifications in conjunction with the engineers to see that, for them to really see how you are solidifying their intuition into mathematics. And as you said, Zoe, maybe integrating more into the process. But I mean, I think that maybe it's convenient for me to put the blame on others, but I do feel like there's also a bit of resistance from the developer community in a sense on that, because they feel that there's a small cost to it and it slows down the development. And often we've experienced some degree of pushback sometimes. So yeah.
I mean, I definitely personally see the value of testing, straight away, right? And automated testing, if it's easy to apply, I think to me seems like a win, right?
For sure, for sure.
So one question I think of here is, like if I think about the developer community and I think about Lean, with my experiences of Lean, is very powerful, but it is also very challenging to use it. And I'm wondering, how you would see that gap being bridged.
Yeah, so I don't see an immediate future without, so in domain-specific cases, sometimes we've been able to develop like enough automation that plausibly with enough training, someone who isn't an expert in interactive theorem proving could actually prove some basic things. So, but for sort of general purpose tasks, that's probably not happening tomorrow, certainly. But what I do think is nice about Lean, and that makes it more accessible than many other interactive theorem provers, is that it has this elaboration step, where essentially, so Lean compilation has multiple steps, and the first one is called the elaboration, where basically the vernacular, the high-level language, is compiled down to a core syntax. And the thing is, this elaborator is itself arbitrarily meta-programmable inside of the language. And so basically, I can give arbitrary strings of Unicode meaning, right? And that means that
you can embed domain-specific languages, for example.
Yes, yeah. And with arbitrary Unicode, and so in particular with like maths, we can get, you can have a sum over a set and with some function and these sorts of things, and we can write it in a notation where I can show my friends who are, mathematicians, have never touched a programming language in their life, the statement of a proposition, and they'll understand what it means. They won't understand a word of the proof, but they will understand the statement itself, and I think that in itself is a step in the right direction.
Yeah, okay.
The other side of it is that if you have Gen Z developers, some of them will use emojis as variable names, and
There's nothing wrong with that.
Hard disagree.
Cool. I don't know if any of you guys want to add anything more to that about bridging that gap.
One can build automation inside theorem provers. Someone could offload things from the theorem prover to an SMT solver. Things have been done in this direction. Not very it's not very widely adopted, but there is stuff to do there. Another thing that I've been thinking for some time now is integrating AI into the proof process. Because AI can write pretty good dumb code, and there is a very well understood syntactic correspondence between writing code and writing proofs.
Yeah,
so if AI can write pretty good code, they can write pretty good proofs.
And you've got the advantage, of course, that if it writes it, you can check it, right?
Yes, exactly. You don't have to trust it, and you don't even have to trust the code that it writes. If it writes the code, it writes the proof. You check the proof. If it works, happy times. So I think there's stuff to explore there, not only in the Ethereum ecosystem or blockchains, but in general. I think that's a very promising direction for formal verification.
Yeah. Okay, thanks. Okay, we'll get back onto the script. So focusing now on the Ethereum ecosystem itself, and so you've all applied formal verification at different levels of the stack in different areas: ZK, smart contracts, consensus. So I'm wondering, where do we feel where can formal verification have the most benefit in the Ethereum ecosystem? How do we feel like where is that kind of sweet spot where the cost value benefit is best? Thoughts?
For me, the answer is obvious. It's infrastructure level stuff, right? So like ZK verifiers, checkers, these sorts of things where there's going to be a huge amount of the ecosystem whose value will flow through that. And if that is exploitable, it's a sort of a single point of failure where just everything will break, right? And so cryptography, obviously consensus, these sorts of things, right? Contracts that things like wallets and these sorts of things that mediate a lot of value flow. I think that's really the place to focus, yeah. And of course, these pieces of infrastructure tend to change less over time than, say, like some DeFi smart contract or something that is sort of an active development, shall we say.
Yeah, and I guess you would say that for example, thinking about ZK EVMs is just a good example in this case, that it is possible to verify at that level. Like some people may see it as actually something that couldn't be done yet, but actually it is possible to have success there.
Yeah, absolutely. I mean, we haven't worked on ZK EVMs specifically. We've worked actually mostly on RISC-V ZK VMs. But yeah, I mean, we have actually, I would say, pulled off some fairly significant results. So as of yet, because in Lean there isn't a full RISC-V spec yet, so we haven't done like a full stack verification yet. But like for RISC-0, we verified some very important parts of the instruction decoder, making sure that it matches the formal spec. We've verified some important parts of the ALU, these sorts of things. And yeah, it can be done. And I think EF is currently, as everyone on this panel is probably aware, funding a fairly big grant program to enable just this. And I think we're probably like at most a year away from having a fully verified RISC-V ZK VM. So yeah.
Cool. Zoe?
I agree. Infrastructure is a huge thing, like to have formally verified code, because it's easier like to have experts doing that, and it's very important, and it can like inspire others to do the same thing for like user code, smart contracts. Then it's building some discipline that others can follow. For me, it's also verified compilers and languages with well-defined semantics that people like use to write code that they understand well. That's the first step, and then they can verify it.
Yeah, so for example, the Solidity compiler would be an example. There certainly have been a number of significant bugs in the compiler, and trying to eliminate that would be super helpful.
Yes.
Yeah. And also, I guess, in terms of smart contracts themselves, there are a number of kind of fundamental contracts, like the deposit contract, and I know that there are a number of contracts coming out for the Pectra upgrade for EIP 7002, for example. Those kinds of things are high-value targets, I guess.
Yes, and it would be extremely good to have reference implementations, at least, that are verified, if not the actual implementations. That would be even
And it would be nice to see, like in the EIP document itself, for example, to see some reference to that, to say, yes. We have invested in formal verification.
Yes.
Maybe, I don't know, some of the artifacts, maybe some proofs, or I'm not sure, but something so it was more visible.
Yeah, totally.
Cool, thank you.
Yeah, I mean, we have seen quite a bit of success in smart contracts already, I guess, so maybe you shouldn't invest that much into them. I don't know. But the smart contract people disagree, I guess, right? Obviously, consensus, yes, but also I would say it's kind of whatever you cannot write in code, these should be verified. Because there are a lot of hidden assumptions usually about timing, about interaction of different components, and this is usually written in English, right? You can write it in code, but it becomes tricky because there is non-determinism, there are some kind of external inputs which you cannot control. So this kind of stuff that is usually written in English, I think it really requires some kind of, if not complete verification, but at least specification and an attempt to understand whether all these constraints that we have in mind, whether they make sense. Maybe they're even contradictory.
So you're almost describing a sort of a mind shift away from writing our specifications in English, sort of predominantly in English, towards making something that can be mechanized. Even if the individual doesn't do the mechanization, at least other people can then do it, right?
Exactly, exactly. I mean, there are a lot of hidden assumptions in many of these protocols because we try to like go from English to TLA, and you uncover a lot of things. Yeah.
So in terms of consensus layer protocols, are there any sort of mechanized protocols, for example?
I mean, there were some proofs in Coq, I guess. Raft was proven to be correct in Coq, as far as I know. Paxos in TLA proof system, it was proven correct. And for the rest, I guess, model checking, what we did, at least showed some results for small parameters, which is also an achievement because it's hard to do it for the general case. Yeah.
Okay, cool. Thank you. Okay, so just now moving into the sort of final part, which is, I guess, looking a bit more into the future. So I guess, how do we imagine the role of formal verification evolving within the Ethereum ecosystem? Like, where are we going from here? What do you think? How do you see it going?
I guess it's me.
Looks like it.
Yeah, I'm not gonna lie. I don't have. As I said in my previous answer, right? I think it is absolutely because, like, it seems that the Ethereum community, their goal overall is to, I think, at some point in the future, be a significant, important part of mediating the transfer of value of our society as a whole, right? And so, if that is the case, and we have, so many of our interactions mediated through this system, it can't go wrong. Like, there would be very serious societal consequences if we got to that point and things go wrong. And so, yeah, I do think that if that is really a goal for the Ethereum community, that they should continue pushing this, and particularly in the infrastructure.
I mean, okay, I'm going to push back a little here,
please.
actually, because I feel like, your answer is sort of idealistic in a sense, right? And
completely.
I'm interested. I'm interested in, like, but where do we, are we actually on that trajectory? Like, is that the direction that we're going in at the moment? What do you think?
I think that's a question more for the Ethereum community and less for me.
You are part of the community, no?
I am, of course, but I work on something pretty niche, and in terms of there are people out there who are looking at all sorts of governance problems, how these can actually be used to, in a decentralized way, actually manage real resources in the real world. And I'm not. This isn't a focus of mine to understand these sorts of things, right? So I wouldn't consider myself an expert, but as I said, I do think that certainly if I do feel that this is, from things I've heard from people in the community, this is a significant goal of the community. And if that is to be the case, well, we should really make sure that it's actually correct and safe, and we're not going to suddenly wake up and, all of our, accounting of value is completely lost as a society, right?
Okay.
I think within the Ethereum ecosystem, the adoption of formal verification is quite impressive compared to to the industry in general. So that's great. So that's the thing that attracted me to the space in the first place. And I think going forward, so I mentioned this before, but I think it will be quite important to build languages with verification in mind, like clean semantics, like well-defined semantics, rich type systems, support for verification, for writing specifications. I think this will be quite important going forward to people who haven't heard about formal verification before, to start adopting and building a mental model for it and being convinced that it's something useful.
So really, Ethereum has actually made a really good start so far.
Yeah,
That's what I'm hearing.
Totally.
And it's really about, as we move to that next level, really trying to push it further into all of the languages and systems that we're using.
Yes. Yeah.
And I know that they are, for example, interested in looking at Solidity and trying to think about what they can do there. So that seems like a really good opportunity for that.
Exactly. That's an amazing opportunity that we have in front of us to make the adoption even wider. And it will be very important for people who are not experts in the field to start learning it. So building the right tools, the right languages, and also training people to use them.
Cool. Thank you.
Yeah, I also have an impression that Ethereum is probably the blockchain ecosystem that has the most adoption of formal methods. That's like my impression, and that's really cool. Yeah, I think I would say yes, we should apply formal verification everywhere, but it's impossible, right? It's just too much. We should focus on the most critical things first, right? That's obvious. But maybe what is less obvious, we should also give small examples of what works. Because what I have seen in TLA Plus, people complain that, okay, you have these huge specifications of consensus. It's so hard to understand, we don't understand what consensus is. Can you give us a simple example, like a dining philosophers, or like this river crossing puzzle, you know, and show how it works step by step. So I think it's also important, you know, to build this bridge between the developers and users and formal verification people to show small examples.
Yeah, so that's about sort of spreading the word about formal verification in kind of easily understandable chunks rather than only having these big examples that are very difficult to get
Exactly.
into.
I mean, if you look at proofs written in all the Ethereum provers, you don't know where to start, right?
Yeah. Cool. Okay, we've got a few minutes before we go into the Q&A. So I will just dig into one more thing, something that I've kind of heard on the grapevine when I've been here in Devcon. So, you know, it seems at the moment, you know, many people doing formal verification related work are working, you know, doing sort of auditing of, you know, systems, but contracts, ZK systems and so on. But it does seem like in many cases, you know, people coming to audits, you know, they don't have specifications for sure, but they also don't even, for example, have test cases sometimes because, you know, they're pushing it to the wire so much. And so it does feel to me like, you know, if we're struggling to get people to write like tests, then we're going to be struggling to get them to do formal verification. And what can we do about this? How do we address this? Thoughts? It's a difficult question. Who wants to go first? Yeah, go on, Kansa.
They should absolutely write specifications and test them. It should be mandatory. Yeah. So building nice, I mean, fuzzing, property-based testing, like this will be quite important. And like it's the first step towards like formally verifying, like formally specifying, testing the formal specifications, and then moving to formal verification of these specifications is it's the right way to go. I mean, you cannot start by formally verifying a spec. You have to convince yourself that it's true, and testing is a very good way to do
So it's
it.
a key stepping stone, really.
Yeah.
Okay.
Yeah, I mean, maybe I can add. We were also doing audits when I worked at the company and now even, right? And at some point I was thinking like maybe we should even require that if you don't have an English document describing what you are doing, we even don't do an audit for you. If you don't have tests, we don't do an audit for you. Because it's an absolute requirement. If you don't have tests, it's just, you cannot do anything, right? It's most likely broken if you don't have tests. Very likely, right?
I mean, it's obviously hard for companies in a position where, you know, they want to take on clients and so on. Like they are, I think at the moment, sort of managing that by adding tests themselves or, you know, reverse engineering the specification in some cases. I mean, in some sense, it raises the costs of the audits as well, you know, like if that's part of what you have to do before you can even do any formal verification. Yeah. Okay, thank you. Julian.
So, yeah, I mean, I'd like to echo what Zoe said. If anyone in the audience, we were talking about you, stop it. But yeah, and also, as you said, yeah, I mean, we have faced some interesting situations with clients who obviously in this situation will remain nameless, where they've told us, hey, here's something we want you to verify. And then when we've asked them about it, they've said, well, we actually don't know how this works anymore. The people who wrote this left. And it's literally, we've had to reverse engineer fairly complex pieces of, well, I'm not going to give too many details once again, but we've had to reverse some fairly complex pieces of software because just the client themselves didn't know how this thing worked anymore. And yeah, it's a problem. But yeah, the other thing that I kind of wanted to float with the other panel members was one thing that I've been thinking about recently is that like modern proof assistants now offer the ability to embed like very fully featured DSLs into them. And one thing I have really been thinking about, so particularly in the context of consensus, right, is that it feels like the lingua franca for a lot of like consensus research and specification is like a simple subset of Python. And we've been thinking of like embedding this into Lean so as to be able to then reason about safety and liveness properties. And that is a way that maybe that we can create, you know, a tighter feedback loop and a closer relationship with the developers through this sort of thing. So just an idea I've had. I don't know if that resonates with you guys at all.
Yeah, totally. Okay, so I think that probably ends the formal part of the panel, and we'll now move to the Q&A part, and I guess there were questions from the floor.
Cool.
Thank you, and please give a big round of applause to our panelists. As a PhD researcher myself, I also kind of value when people like make time in their schedule to come out and talk with the community about their experience and expertise. So we have quite a few questions, and I think the panelists covered most of it, but still, people in the audience are not convinced, like, why should we go and do this extra step to implement formal verification? So the first question would be, please share the elevator pitch to engineering teams to implement formal verification as a hard gate that care about the velocity of shipping code. And how can we make this easy for engineering teams to lean in and do this method? So if anyone...
So writing code that is correct and does not introduce unexpected failures is like the elevator pitch, I would say. It's something very valuable on its own end. And then, again, like, I really believe in writing spec and testing it before anything else. So if anything that we can do to convince engineering to write better code is like specifying it, formally specifying it with like some specification language, and then testing the specification. And then that would be a great step already towards having better code in like a viable time frame, not like spending 3 years to verify a piece of code. Well, this happens a lot. I think to all 3 of us at least, this has happened, or 4 of us. Yeah, so I really believe in the value of specification. Yes. Yes, that would help immensely to have native support from the language, that it's a language that people use, and like it's like a common ground for everyone to like, yes, it's not something niche, it's not a weird tool that very few people know and understand. It should be something that is widely adopted and has support for writing specs and clear formal semantics. Okay, next question is kind of similar. What metrics are used to measure impact of formal verification on the security and reliability of Ethereum? If you can maybe give us more information, how can we measure the impact of formal verification? I think it is what Julian said before, like if it works, nothing happens, right? So,
yeah. I mean, you can also, so certainly, when we formally verified things, we have at times found some fairly serious bugs. And so certainly you can, when you do find these bugs, you can sort of evaluate the impact in terms of, hey, what would be the worst case scenario here, right? And certainly, we found bugs in ZK proof systems, we found bugs in DeFi smart contracts, which would have potentially allowed them to be completely drained or frozen, and these sorts of things. So there's perhaps an economic value that you can put to it, but as you said, once again, what we do is making sure that things don't go wrong, and so it's difficult to quantify hypothetical futures or hypothetical, parallel presents in which things went very wrong.
Yeah, I mean, one thing I have seen in consensus, which is very cute, you can actually just add a bit more faults, and in this case, the algorithm should break. And that's like very easy to show people. Like, just have one more fault, see what happens. It crashes all possible ways, and that's like an easy metric. But another metric, like in code verification, is just how many bugs you have found, basically. And there is like another metric which is saying how fast you have found this bug. Okay, thank you. We still have time, and
also have still a lot of questions. And the next question would be, have you had experience formally verifying ZK proof systems at constrained polynomial level? And to what extent does Lean have to be modified to express theorems in that context?
Yeah, I think I'm the best person to hit this one. So yes, we have done that. How much does Lean need to be modified? Not at all. It has notions of finite fields and polynomials built into MATLAB. Now, we've also actually written some custom decision procedures for finite fields and these sorts of things that do speed up the verifications of these properties. But yeah, other than this, it's mostly actually just extracting from whatever your ZK DSL is, writing that extractor from whatever your ZK DSL is into a set of a polynomial constraint system in Lean. But as I said, there's primitive support for that in the standard library. The one issue that I think is a bit more interesting and where we're hoping for some more language support, particularly in Plonky 3, is that a lot of the ZK DSLs, as they are now, their tool chain is not at all modular. So it goes through a bunch of generation steps, and right at the end, it just dumps you, thousands, tens of thousands of constraints sometimes in one big blob, right? And there's no notion of, oh, this came from this chip, etc. And so one thing that I think will be good in terms of helping this kind of verification scale better, it's more actually on the ZK DSL level, is actually having a better notion of these sort of modular boundaries. This is a chip. These are how these are wired together. Sorry.
So just following on from that, because at the formal verification hangout yesterday, there was mention of, it was called LLZK, which was low-level ZK, which is about bringing a kind of intermediate language that all of these DSLs could compile down to, and then the verification work could come off that. That's sort of what you're talking about?
Yeah, exactly. I think this is actually a great idea. The one issue that I would issue in quotes that I would have with this is at this point in time, the proof systems are evolving so quickly that it's unclear that any DSL that we will write at this point in time is really going to be able to capture all of the constraint systems going forward. But from my understanding, this LLZK or whatever, it seems like very honest, like a very solid attempt by Veridice at doing this for the moment. And I'll be very curious to see their progress. Yeah.
Okay, the next question is, what is the first baby step and tool you recommend for engineering teams to start on a journey with formal verification?
Well, I mean, most developing teams are already using formal verification to some extent, in the sense that often they use type systems, and that is a very simple form of formal verification, right? And I think, as Zoe pointed out, Rust is becoming more and more popular. And actually, I mean, linear type systems, certainly I think within smart contract development, has actually have a lot of potential, because I mean, most smart contracts are actually kind of about managing resources, moving money from A to B, making sure that I haven't, I haven't double spent any of that money, I haven't not spent any of that money, right? And so I think that there's a lot of, on a very low level, there's a lot of capacity for just using basic type systems to enforce properties that are useful.
I think lightweight verification tools is a great start. They should use HEVM to symbolically execute their smart contracts. It's easy on the programmer's end to convert their tests to symbolic execution assertions and then check them formally with a symbolic execution. So this is my recommendation.
Yeah, I also think simple tools, and I mean no shilling, but you can check Quint. That's the surface syntax for TLA+. It has a random simulator, starts in very easy, I would say, but something like that in general. Yeah.
And one more question: between Viper and Solidity languages, which one is easier language to formally verify? Is the last question.
Can the answer be neither? I mean, neither of these languages have fully formal semantics, right? And so this is a key issue that we have, is that typically you have to go to UL or the EVM to really have formal semantics, to actually have an actual fixed meaning of what the language means. Otherwise, for both of these, really, the language semantics are defined by, well, whatever the compiler chooses they are. And so the answer, at least for me, is neither. You just have to compile them to some other representation, which does have a somewhat fixed semantics and then reason there.
None, I think.
Okay.
But I think there is a huge opportunity here to build languages with formal semantics and verification in mind. I think that's a huge step towards making formal verification more widely adopted in the space.
Thank you very much. Thank you very much. And